Hello, this is 5-7. It was roots and zeros. Okay, so I'm going to briefly go over what we did in 5-7. Okay, so the goal was to determine the number and types of roots for a polynomial, and then find the zeros of a polynomial equation. We started this by simply just talking about examples, noticing that when we have the zeros are the same thing. If I asked you for the roots, so zeros and roots are the same thing. Zeros are the answer to the problem. So if I were to ask you to factor this problem, when you finish factoring it and you set them equal to 0, those would be your answers. Okay, now if I asked you for the factors you just take the opposite sign. So if I give you -3 as a 0, the factor would be x plus 3. Okay, and the intercepts are just the zeros with a 0 at the end. The intercepts are something that we can plot. Our zeros are also known as our x-intercepts. They are where they cross the x-axis. So the fundamental theorem of algebra, what that just tells me is that if I have a 2 as my exponent, that means I should have 2 solutions. And if I were to solve this, what they're asking us to do is just to say, okay, do you have a real root or an imaginary root? This was the culinary, which says the same exact thing. Then we talked about Descartes' rule of sign change. So Descartes' rule of sign change, it tells me the possible numbers of positive roots of a polynomial is equal to the number of sign changes in the coefficients of the term or less than the sign changes by multiples of 2. So that's important, multiples of 2. Now the same is true, the same definition for negative. The only difference is we're going to change it and we're going to be plugging in a negative x. Here's an example. So this is the one that we did in class. So I'm going to go ahead and do this one. They're asking, state the possible number of positive real zeros, negative zeros, and for right now, we're just going to ignore the imaginary zeros of it. So to find the positive ones, I'm going to put positive. I'm going to work with the original problem, and I'm just going to count the sign changes. So this is positive, positive, positive. Then it goes to a negative, so there's one sign change. Then we have another negative, and then it goes to positive. So we have 2 sign changes, but remember, it goes down. The definition said or decreases by multiples of 2. So 2 minus 2 would be 0. So we have a possibility of getting 2 positive zeros, or none of our answers would be positive. Now let's do the negative one. So to do the negative one, what we're going to have to do is, before we do it for the negative one, we need to, don't forget, we got to plug in a negative x. So here's a trick with this. If the exponent on the top here, if it is odd, that means we change the sign of the term. So my new 2x would be negative 2x to the 5th because 5 is odd. 4 is even, so we're going to leave this exactly the same. So it's going to be plus x to the 4th. 3 is odd, so now it's going to be negative 3x to the 3rd. 2 is even, so it's going to be negative 4x to the 2nd, so that stays the same. There's an imaginary 1 there. 1 is odd, so it's going to change to a positive x plus 9. Now we're going to do exactly like what we did with our positive zeros. We're just going to count the sign changes. So negative to positive, that's one sign change. Positive to negative, that's another sign change. Then it's going to stay negative, negative to positive, another sign change, and then positive, positive. So for negative zeros, we have a total of 3 maximum. However, we take away 2, so 3 minus 2 would be 1. And then if I try to take 1 minus 2, if I do 1 minus 2, I would get a negative 1. And I don't want any negative answers. So my possibility for getting negative zeros would be either 3 or 1. And that was finding using Descartes' rule. The last thing that we did in 5-7 was to talk about the complicate conjugate theorem. So it just says that if a plus bi is a 0, that means a minus bi is a 0. Okay, so if I give you a plus bi, you should automatically know that a minus bi is also a 0. And here's an example of that. Okay, we did this one in class. I'm going to go ahead and work it out again. It wants me to write a polynomial function of least degree with integral coefficients, the zeros of which include -1 and 5 minus I. So they give us the zeros. What that means is that they give us the answer. What we need is a polynomial function. So we want to end up with an equation. So if they give me the zeros, well, the first thing I need to know is that they give me -1, 5 minus I, and we just said with the complex conjugate that if I'm given 5 minus I also know that 5 plus I is also a 0. I'm going to go ahead and write these in factored form because right now they are in 0 form. I want to write it in factored form. So x minus -1, the factored form would be x plus 1. Okay, the reason for that, if you think about it, if you factor and then you're solving, you're saying x plus 1 equals 0. And then you minus 1, so x is equal to -1. That's why when we put it in factored form, we take the opposite sign. Then I'm going to say x, and then the opposite sign of 5, of a positive 5 is a -5. The opposite sign of a negative I is a positive I. Then I need my last one. So I'm going to say x. The opposite sign of a positive 5 is a -5. The opposite sign of a positive I is a -I. Okay, so all I did for the first step was just rewrite it in factored form. Now I need to go ahead and I gotta try to make this a little bit simpler. So I'm gonna leave my x plus 1, and I'm gonna clean up our next guys right here. The first thing that I notice is that I have an x minus 5 and another x minus 5. So I'm just gonna write it as x minus 5 to the second. Then I have plus I and minus I. So when I multiply that, I get negative I to the second. Guys, I'm just cleaning this up. I'm going to leave the x plus 1 alone, and I'm going to work with x minus 5 times x minus 5. Now this negative here, this guy right here, I to the second, remember that I to the second is equal to -1. And we already have a negative in our formula. So negative times a -1 is going to give me plus 1 at the end. Okay, from here on out, what we're doing is cleaning this up with multiplying. So I'm going to go ahead and FOIL my first and then my outer. So I'm going to get x to the second and then -5x. Then my inner, so it'll be -5x, and my last, so plus 25, and I still have that plus 1. I'm going to leave my x plus 1 on the outside alone, and now I'm just going to combine like terms. So it's x to the second minus 10x plus 25 and 1 gives me 26. And we're getting close to finishing up. So now is when the x plus 1 is going to come into play. I'm going to distribute the x to everybody. Distribute the x. So it would be x to the third minus 10x to the second plus 26. Then I distribute the 1. So it's going to be 1x to the second. Then I have negative 10x plus 26. Lastly, we just look for like terms. So x to the third does not have a like term, but 10x, negative 10x squared and 1x gives me negative 9x to the second. And then I have 26, it should have been a 26x. So 26x and a negative 10x. That's going to give me a positive 16x, and then my last one would be 26. So this is my final answer. This is a polynomial that if I were to factor and solve this, these would be my zeros. So we essentially worked backwards. And that was it for 5-7. Have a wonderful day.